In the past portion of this lecture, we looked at credit-based systems. We'll now turn our attention to cash-based systems. Cash-based systems offer two advantages over credit-based systems. The first is they provide better anonymity. When you use a credit card-based system, the bank always knows what you're doing because the credit card is issued in your name. When you pay for something in cash, nobody necessarily knows who you are when you purchase something. The other thing that cash can enable is offline transactions, where you don't have to phone home to a third party in order to get the transaction approved. You can give someone cash and the transaction is done and everyone's satisfied. Maybe later they go to a third party like a bank to deposit the cash, but that third party doesn't need to be present in the transaction itself. Now, these two requirements are sort of a more extreme version of what Bitcoin offers. In Bitcoin, it doesn't offer the same anonymity level as cash. In Bitcoin, it offers pseudonymity, which means that some of your transactions could be tied together if you use the same Bitcoin addresses to originate transactions. Bitcoin also doesn't work in a fully offline way. It's true, what you could do is you could create a Bitcoin transaction, you could sign it, you could hand it to someone, maybe email it to them, but that person won't be content that that money won't be double spent until they see that it's incorporated in the blockchain. So unless if you are online and able to broadcast that to the peer-to-peer network, or alternatively you really trust the person that you're receiving the money from, Bitcoin operates in essentially an online fashion. The earliest ideas of applying cryptography to cash came from David Chaum in 1983. To think about David Chaum's proposal, let's start with a sort of predecessor to his actual proposal. So imagine that I handed you a $100 bill, and I also handed you a piece of paper, and the piece of paper was a contract, and it said that whoever comes back to you with this piece of paper, you'll give that $100 bill to them. Maybe you'll give them $99 to keep a cut for yourself. In any case, I want you to sign this paper saying that you will honor that arrangement. And then I'll take that paper with me and I'll give it to someone else. If I give it to someone else, then that paper is effectively worth $100. Now you might be thinking, what's the big deal? All you did is convert one small piece of paper worth $100, the bill, into a big piece of paper worth $100, which is the contract. But of course, this is a physical analogy of what you can do in a digital realm. We are able to do digital signatures, and so this contract could be a digital object. As long as people trust that the person who issued the contract is willing to honor the contract, then the system works. And effectively, this digital contract is worth $100. Now, there is one problem, however. The problem is, once it's a digital contract, it's very easy to copy and paste those bits. So now you have two contracts. If each contract's worth $100, you just doubled your money to $200. If you send those two contracts to two different people, this is called the double spending problem. And double spending is a problem that exists in all eCash systems. All eCash systems have to have some way of dealing with double spending problem, including Bitcoin. So the first attempt at fixing the double spending problem is to encode a unique serial number in each contract. This actually isn't sufficient to completely solve the problem, but it's a step in the right direction. Now, the problem with the serial number is that, remember, one of the advantages of cash is that it's anonymous. But now if you have unique serial numbers, the bank knows who it issued this contract to, and they can write down their name and they can write down the serial number that the contract encoded, and then they can trace this person as they spend the money. So David Chaum came up with the digital equivalent of something called a blind signature, and I'll explain it more in paper-based form. To understand a blind signature, you could imagine that we take this contract, but in this case, instead of it being printed in normal ink, we print it in invisible ink. Okay? So the bank, we take it to the bank and we say, will you sign this contract? And they can't actually read what is written because it's in invisible ink. So the ink is providing two properties. The first is, the obvious property, is that it hides the information that's in the contract. But the second property, which is equally important, is that whatever I printed on that contract in invisible ink, I can't change it. It's locked in, it's fixed. And so if the bank decided to expose it to see what actually was written there, then there's no way to change it. Okay, so this is called the binding property. So this solution obviously solves the problem of the bank seeing your serial number. The bank doesn't see your serial number. However, it creates an even bigger problem, which is the bank doesn't see anything about the contract at all. It has no idea that it encodes the fact that it owes someone $100. The contract might encode the fact that it owes someone $1 million. So the bank wants to be convinced that this contract is formed correctly, that the amounts are correct, but the paradox is it can't see the serial number. Now, one solution to this might be that only the serial number is printed in invisible ink and the rest of the contract is printed in regular ink. So the bank is content, they can see what the amount is, and the user is content because they maintain their privacy. The problem with this is at a cryptographic level, when we transition into digital signatures, we didn't, at least in the early 80s, we didn't know how to do this. Blind signatures back then were all or nothing. Either you hid everything that was being signed or you hid none of it. And so we needed a different solution. So the question is, how can I convince you to sign something if you can't read it? And the answer is we can use what's called a cut and choose protocol. In this protocol, what I would do is I would create 100 contracts and hand them to you in a stack. What you would do is you would pick one at random from the stack and you would reveal the invisible ink. And when you reveal it, you can check that at least for that contract, yes, it did encode the fact that you owed $100 as opposed to $1 million. Then you can pick a second contract out of the pile, you can reveal it and make sure it also says $100. You can keep doing it until there's one contract left, okay? When you have this one contract and you're holding it, even though you don't reveal the invisible ink, because the other 99 all said $100 and you chose them randomly, you're pretty sure that this one also encodes $100, and so you sign it convinced to at least to a 99% probability that it actually says $100. So how does this help with the double spending problem? Well, the cut and choose protocol allows the bank to sign a contract, be convinced that it encodes the right amount, and yet not be able to see someone's serial number. So the idea is that you would get granted one of these contracts. When you wanted to do a transaction, you would give this contract to the person that the merchant that you're buying the goods from. And then the merchant would turn around and give it back to the bank right away. So in Chom's earliest system, this was an online transaction system where you had to phone home to the bank every time you received one of these contracts. And we can stop calling them contracts, we can call them coins, because that's another term for what they actually are. And so when you spend a coin, the merchant goes to the bank and they give it to the bank and they ask the bank, have you seen this coin before? Has it come in before? Has this serial number been spent before? And if the bank says no, it hasn't been spent before, then they honor the coin, the contract component of the coin, and they give the merchant the money that's owed. If the merchant goes to the bank and it has been double spent, then they can at least detect it. Now the problem is that if it is double spent, you have no idea who the buyer is because it's an anonymous system. So that's a drawback that people worked on later to address. Another drawback of this system is that once you spend a coin, you can't use it again. So it's not like an actual cash system where you mint coins, you hand it to the first person, they send it to a second person, and then the second person can give it to a third and a fourth, and you can have a whole chain of transactions. In these type of system, every time you receive a transaction, you have to go back to the bank and essentially cash it in. Now the bank might issue a fresh coin, that's fine, but the point is that these coins are only living for one transaction at a time. Now one proposal at fixing the problem that the bank has to be online at all times came in 1988 from Chom along with Fiat and Naor. What they observed is that if you want to prevent somebody from double spending a digital object, it's really hard. It might be impossible. There's no way to stop people from copying and pasting digital strings. However, they also noted that in traditional finance, we have this idea of checks, and the same problem arises. If I write you a check, you have no guarantee that the money's actually in my account. Maybe the money is in my account. I write you a check for $100. I have $100 in my account, but there's nothing stopping me from writing a second check to someone else for $100, in which case if both of you try and cash it, then one of you won't be able to cash it. So in order to stop bad checks from circulating, what the bank system uses is a detection system as opposed to a prevention system. They don't try and stop you from writing that second check, but what they do is when you write that second check, they are able to detect that it exists. They know who you are because you have a bank account with the bank, and they'll punish you through a penalty for doing that. And so the idea of Chom, Fiat, and Neor is there some way to do that type of system in the digital realm? So if we go back to the idea that coins encode a unique serial number, we can think about what this serial number looks like. If the bank maintains a mapping between customer names and serial numbers, then there's no anonymity in the system. Every time a coin comes back to the bank, they know who it was that spent it, and since the coin is coming from a merchant, they know where that user spent the money. In the original Chom 83 scheme, the serial numbers were just random numbers. Okay, there was no link between the serial number and the bank. In fact, the bank couldn't even link them because of the blind signature. It hid the serial numbers in the coin, so the bank didn't even see the serial numbers. In this case, it offers full anonymity. Now the question is there something in the middle between having no anonymity and full anonymity where we can allow partial traceability of coins, particularly in the case where they're double spent? So what Chom, Fiat, and Neor came up with is the idea that every coin would include 2 serial numbers. These serial numbers would be arranged so that when you add them together, it actually forms the identity of the person who withdrew the cash. Now, this is a more general description of what this technique is secret sharing. So in a secret sharing scheme, you have a secret and you split it up into n shares, you give it to n people, and you do it in such a way that if any m of the n, where m is some number less than n, as long as m people come together, then they can reconstruct what the secret is. So you can think of this as a 2 out of 2 secret sharing scheme, but there's any possibility for n and m is also possible in the system. So the idea is you would still go to the bank as normal. You would give them a contract just like in the previous scheme. The only difference is that there would be 2 serial numbers. Now the bank would do the cut and choose. You would hand them 100 coins and they would open up 99 of them. And when they open the 99, they would check that those 2 numbers also add up to your actual identity. So they're certain that in the contract they sign, the coin that they sign, that those 2 numbers will also add up to your identity. So the idea is when I spend a coin, I give it to the merchant, and these serial numbers are still hidden. The merchant has no idea what the 2 serial numbers are, but what the merchant can do is they can ask me to reveal one or the other. You can think of it as the left serial number or the right serial number. So they might flip a coin and ask me to reveal it. So what happens if I just spend the coin once, which is what we want to encourage, they only learn half of the secret. So they're either learning a random number or a random number minus my identity, which is also a random number that's fully masked. And so it doesn't reveal any information about my identity. Now, if I double spend, if I send that same coin to a second merchant, one of 2 things can happen. The second merchant will also go through the same protocol. They'll ask me to either reveal the left share or the right share. Assuming the first merchant asks for the left share, and if the second merchant also asks for the left share, then what happens is my identity still isn't revealed. Okay? Now, when both of those merchants cash in their coins, the bank will detect that double spending occurred, but they won't have any idea about who actually did it. However, 50% of the time, the second merchant will ask for a different share than the first. So if the first asks for the left share, the second might ask for the right share. In this case, when they both cash in their coins at the bank sees that it's double spending. Because they have different shares, they can add those shares together. Now they know the identity of the person who did the double spending, and they can leverage some fee or punishment against that person. Now, 50% chance of catching double spending isn't that great. And so is there any way that we can boost this? So the idea that Chom, Fiat, and Neor had is instead of encoding 1 pair of numbers, what if we encode, say, 10? So for example, let's assume that they have a table, and here's my real name, and they assign a serial number to my name, 31337. And so here's a list of 10 numbers, 10 pairs of numbers, and if you do the mental arithmetic, you'll see that in each case they add up to this number. So what happens is when I spend a coin, these numbers are originally hidden, and the merchant gets to go through the list and they get to pick from each pair whether they want to see the left number or the right pair, but they do this for all 10 instead of just one single pair. So for example, the merchant might ask for the left, the left, the right, the left, and so on. Now when I go to a second merchant, we do the same protocol. They're initially hidden, but the second merchant gets to also for each pair ask for either the left or the right. And what will happen with overwhelming probability is that at some point going through these pairs, the two merchants will ask for different shares. So for example, in the second row, and also in a lot of other rows in this example, if they ask for the left share and the right share, and in that case, you can add together those two shares and reveal the identity of the person who spent the money. And so this works to boost the probability from 1/2 to actually any number that you want. If you have n rows or n pairs, then the probability of getting caught is 1 minus 2 to the minus n. And so it goes up to, for example, 99.999% if you use 20 pairs. Now, this doesn't solve the problem of being able to spend a coin more than once. Once you spend your coin, the merchant still has to go back to the bank and they have to cash that coin in. And you can think about why. Why can't the merchant accept a transaction and then take that coin and turn around and spend it? Well, the answer is that that coin encodes the identity of the original spender. Okay, so if the merchant were able to respend that coin, then let's say they double spent it, then it would be the original person who was issued the coin whose identity is encoded in that coin. Now, you might also think, is there some attack here where I receive a coin and then I turn around and try and double spend it to falsely blame the person who gave it to me? But because I don't know what the other numbers are that are hidden, I only know the one path of opening up the pairs. That's all I can do if I turn around and try and spend it myself. I can only open up the same pairs. Now, there's a couple ways we can improve this protocol. One thing is the efficiency is really bad. If we think about the idea of using 20 pairs of serial numbers, in that case, we have 40 serial numbers, okay, 20 pairs. But remember, when you go to the bank initially, you hand them, say, 100 coins, and they're going to open 99. Now, in that case, they have a 1% chance. You have a 1% chance of deceiving the bank, and that's probably too high. You probably want it a lot smaller than that. So you're more likely to go to the bank with 1,000 coins or 10,000 coins, and they're going to open all of them but one. And so if you think about serial numbers, 40 serial numbers on each coin, and then you're handing 1,000 coins, you're handing over 4,000 serial numbers to the bank. So this is a large digital object that you're giving to the bank to audit. So what happened over the ensuing years is that a bunch of cryptographers look at this problem, and sort of in parallel to this eCash systems being developed, there was some advancements in an area called zero-knowledge proofs, which we're talking about in the earlier lecture in this series when you talked about Zerocoin. In this case, they slowly replace all these cut and choose with more compact zero-knowledge proofs. So it's very easy. You just go to the bank, you hand them one contract, and then you prove in zero-knowledge, for example, that encodes 100. And then you're done. You don't have to give them 100 coins. You just give them one, and the proof is very succinct and it's short. Another area of research was the idea of adding divisibility to the coins. So in Chom's original scheme, in Chom, Fiat, and Naor, if you got issued a coin that was worth $100 and you wanted to buy something that was, say, only $75, there was no way to split that coin into 75 and 25. All you could do is go back to the bank, cash in that $100, and ask for a $75 coin and a $25 coin. So Okamoto and Ota, they had some interesting ideas. It used Merkle trees, which show up in Bitcoin, to create a system that was divisible, where you could actually subdivide the coins that you were issued without involving the bank in the process. Now, Chom took his ideas and he commercialized them. He formed a company in 1989 called DigitCash. And this was probably the earliest company that dealt with online transactions or tried to solve the problem of online transactions. They had about a 5-year head start on other companies like First Virtual and Cybercash that we talked about in the earlier lectures. The actual cash in their system was called eCash, and they had another system called Cyberbucks. And there were a couple of banks that actually implemented them. There were a few in the US, there was at least one in Finland. In this case, in the eCash systems, because it uses Chom's protocols, clients are anonymous. So the bank can't trace the money. When the money comes back, the coin comes back, it has a serial number, and the bank doesn't know which user's serial number that was issued to. However, the merchants aren't. The merchants, because they have to return coins as soon as they receive them, the bank knows all the information about the merchants, how much money is coming in at what time, etc. This is what the screenshot looked like from the software. And so you can see here there's a wallet, and it shows you your balance. And then here's all the coins that you have that have been issued to you from the bank. And because you can't split coins, because there's no way to split them up, what the bank does is they issue you a whole set of coins in different denominations. So for example, you might get 8 pennies, 8 2-cent coins, 8 4-cent coins, et cetera, so that you can always sort of reconstruct the right amount of change to pay for the exact amount of a transaction. When you filled out a transaction, what would happen is you would browse to a website. So for example, this is to make a donation to Epic. And if you wanted to donate the money, you would click the link on the website. And what it would do is it would open a server connection back to your computer. And so your computer had to have the full ability to be online and accept incoming server connections. It had to be running HTTP and have a port open to receive it. You had to have a full IP address. And if it was successful, the connection was successful, then your wallet service would launch on your computer, and then you were able to approve the transaction and send the money. Now, there were certain variants to DigiCash that were pursued. One thing that was sort of controversial about DigiCash is that the technology was patented, and specifically the blind signature scheme that was used had a patent filed on it. And so that stopped other people from developing eCash systems that used the same protocol. There were a bunch of cryptographers that hung out on a mailing list called the Cypherpunks mailing list. This later transitioned into the cryptography mailing list, and you'll know the cryptography mailing list as the place where Satoshi originally posted the white paper and introduced Bitcoin. But before it made that transition, the Cypherpunks, they implemented a version of eCash, of David's eCash, that was called Magic Money. And Magic Money was only for experimental use, so it did violate the patents, but because it was non-commercial, you could use it to experiment with. And it was sort of a fun piece of software to play with. The interface was all text-based. You could send transactions by email. You would just copy and paste literally into email. Hopefully you'd use a PGP key to protect the transaction in transit, and you could email it to another user. The other user would import it into a file on their computer, which was called allcoins.dat, which sounds a little bit like wallet.dat, which is what Bitcoin uses to store its coins. Another proposal by Ben Laurie, with contributions from lots of other people, is called Lucra. And in this scheme, what they did is they targeted the blind signature scheme, and they tried to come up with an alternative which wouldn't be covered by the patent, and then you can keep the rest of the system largely the same. Another problem that's interesting that arises when you use DigiCash is, as we mentioned, you can't make change. And so if you need to make change, you have to go back to the bank, and you have to get the bank to reissue the right set of coins so that you can make exact change for something. Ian Goldberg had the idea that maybe the merchant could send you coins back if they had some coins, so that you might overpay for the item, but then you would get some coins back. However, this introduces a problem with anonymity. Remember, in eCash, the senders are anonymous, however, the merchants aren't. And when the merchant sends cash back, technically they're the sender, so they're anonymous, and you, as the person who has to turn this cash into the bank, are not anonymous. And so there's no way to do that system without breaking the anonymity of the original user trying to buy the goods. And so he had a different proposal where there were different types of coins that would allow these transactions to occur, allow you to get change back, and preserve the anonymity of the user. Now, why did DigiCash fail? The main problem with DigiCash is it was hard to persuade, the banks and the merchants to adopt it. People didn't want to use it, and because no merchants, or not a lot of merchants, were using it to accept money, then users didn't want to use it either. It also didn't support user-to-user transactions. At least it didn't support them very well. It was really centered on the user-to-merchant transaction. And so if merchants weren't on board with the system, then there was no way to really bootstrap interest in the system. As a side note, Bitcoin, because it allows both user-to-merchant and user-to-user transaction, Bitcoin probably, part of its success could be attributed to the fact that it supported user-to-user transactions. So there was something to do with your Bitcoin, at least send it to other users, while the community tried to drum up support for Bitcoin and get merchants to accept it. So at the end of the day, DigiCash lost and the credit card companies won. In the later years of the company, DigiCash also experimented with tamper-proof hardware, or tamper-resistant hardware. In this case, they had devices. They might be a small device that was usually called a wallet, or it might be some sort of card. And what they were trying to solve is this double spending problem. And in this case, they weren't trying to just merely detect the existence of double spending. They were trying to actually prevent it. So in this hardware, there might be a counter that encodes your balance, and every time you spend money, the counter decreases. If you load the card with more money, then the counter goes up. But the point is, there's no way to physically or digitally go in and tamper with that counter. So if that counter goes to 0, then that card stops being able to spend money. Now, there were a bunch of companies that looked at this tamper-resistant hardware in addition to DigiCash. DigiCash worked later with a company called Café, which was based in Europe. There was also another company formed called Mondex that was later acquired by MasterCard. And Visa had their own variant called Visa Cash. So this is the Mondex system. Mondex consisted of a card. This is a smart card with a chip. And there were also these wallet units. And you could load either of them with cash. So you can get the cards and they would have some amount of cash on them. And you can have wallets that would also have cash on them. And if you wanted to do a user-to-user swap of money, what would happen is the first user would put their card into the wallet. You could move money off of the card onto the wallet. Then you'd stick the second card in the wallet and you move the money off the wallet onto the second card. And so you could exchange cash in that way, and it was anonymous. Now, Mondex actually trialed their technology in a bunch of communities. One community is actually a city very close to where I grew up in Guelph, Ontario. And needless to say, because it doesn't exist today, this technology, you know what the end of the story is, which is it didn't really catch on. And the main problem with it is that cards, Mondex cards, they're like cash. If you lose them or they get stolen, the money's gone. And if there was some sort of malfunction with the card, if the card reader wouldn't read it, there's no way to determine whether that card had balance on it or not. And so Mondex, typically what they would do in these scenarios is they would incur the cost. They would assume that, that the card was loaded, and then they would re-enumerate the user for that lost money. But that cost the company a lot of money. The wallet itself was also, it was sort of a larger form factor. It was slow in order to process. It was much faster to pay with credit card or with cash. And retailers hated having a bunch of these terminals. They just wanted to have one terminal for your Visa card, and they didn't want to have two different terminals. So for all of these reasons, the Mondex experiment was not successful. However, what was successful is, if you remember these cards, we have these small chips on them. And so this is a smart card technology. Today, in a lot of countries, including Canada, where I live, every single credit card and every single debit card now has this technology on it. They all are based on smart cards. It's used for a different purpose. It's not used to prevent double spending. It's used for authentication. So you prove that you know the PIN that's associated with your account. But this technology was adopted, and Mondex was using it long before the wider banking industry made it a standard for bank-issued cards.